Boston University today, and I don't want to hold it up any longer. So welcome, Ksenia. Good morning, and let's start the talk.
Okay, thank you very much. Thank you very much for introduction, and thank you very much to organizers for giving me the opportunity to share some of our recent results. And today I'm going to talk about okay, so my slides only go one way. Okay, today I'm going to talk about how one can extend multi-reference methods and even more broadly, in principle, any multi-state technique to describing electronic resonances. So first of all, what are electronic resonances or metastable electronic states? So those are electronic states that lie above ionization threshold or detachment continuum. They can be prepared in multiple ways. It can be excitation above ionization threshold, for example, as shown here for a neutral molecule. So we have neutral molecule AB. It can get excited above ionization threshold, and resulting excited state is going to be metastable with respect to electron decay. Or it can be, for example, formed upon electron scattering on a neutral molecule. If electron attachment is a downhill process, the result will be a formation of stable bound electronic state. But if electron attachment is an uphill process, the resulting anion will be metastable with respect to the loss of electron. So what fundamentally distinguishes these metastable states from the bound electronic states is they belong to the continuous spectrum of the electronic Hamiltonian. And the consequence of that they have intrinsically finite lifetimes. So if one wants to describe the processes for that go through formation of this metastable electronic states, one has to have information of both energies of the states and their lifetimes. And it might seem rather rare electronic structure, but the states are actually quite ubiquitous. So they are commonly found in high energy environments such as plasmas. They can be formed in plasmonic catalysis, for example, upon electron capture by a reactant H2 molecule on the surface of gold plasmonic nanoparticle. H2 minus will be metastable with respect to electron loss. Core excited and core ionized states are examples of metastable states. They can decay through Auger relaxation or related mechanism. And once again, so if we are to describe spectroscopy related to these electronic states or chemistry that proceeds through formation of this metastable electronic states, one has to have additional information, not just on the energy of the states, but also on their lifetime. So this is what I'm going to talk about today. So how one can extend powerful methods that have been developed for bound electronic states, in particular multi-reference methods implemented in MOLCAS to describing of a description of metastable electronic states. And the technique that we use to do this is complex absorbing potential. So I will first introduce what this method is. So projected cup formalism is a model that actually allows us to effectively extend the methods that have been originally developed for bound state to resonances. So I'll introduce this model. And then I'll describe this open cup software we developed to extend existing implementation of multi-reference methods and in general multi-state methods that have been developed for bound electronic states without alternation of their software implementation to a description of the metastable electronic states, and show how does it work. All right. So there are multiple methods groups of methods that allow for description of metastable character of electronic states. Non-Hermitian quantum mechanics approaches are particularly attractive as they convert metastable state into a single square integrable state, and therefore one can imagine they allow for rather straightforward integration with the methods that have been developed for bound states. So complex absorbing potential belongs to this group of methods. In this case, we start from electronic Hamiltonian, and we augment it by purely imaginary potential, where W determines the functional form of the absorbing potential, complex absorbing potential it's called, and eta determines the strength of the absorbing potential. So when eta is 0, we recover original Hermitian electronic Hamiltonian. So the resulting Hamiltonian becomes non-Hermitian, and resonances appear as single square integrable state of cup augmented Hamiltonian. associated with complex eigenvalue, where real part of this complex eigenvalue gives us resonance energy, and imaginary part of this complex eigenvalue determines the width. So in principle, if we can get eigenvalues of this kappa augmented Hamiltonian, we can get both parameters of the resonance state, so their energies and their width, which is inversely proportional to lifetime, so lifetime. So how KAP changes, for example, eigenstates of electronic Hamiltonian is what is illustrated here for model one-dimensional potential. So red is Rosen-Morser one-dimensional model potential, which supports single resonance state, so it doesn't have any bound state. It supports single resonance around 0.5 atomic units. And what is shown in the black are bare eigenstates of electronic Hamiltonian obtained in some finite basis. And what we see is happening is that there are multiple states with notable amplitude inside the well. They still have scattering tails outside. Beyond that, so we have just scattering waves. The higher we go in energy, the greater is the frequency. So this manifold of states are with notable amplitude inside the well represent resonance, and the denser is the basis we use for description, the more of them we will get. So in principle, we have continuum of states with somewhat character like that, some amplitude inside the well and scattering tails outside. So once we add absorbing potential, so this purely imaginary potential, functional form is typically such that it's zero close to interaction region, or in case of molecules close to molecular region, then it has rising typically quadratic form to absorb the scattering tails of resonance wave function. So once we add KAP to the Hamiltonian and now look at the results in eigenvalues, we will see that we have only single eigenstate associated with resonance, which have notable amplitude inside the well, pretty much no scattering tails outside. So this is how the resonance wave function would look like in the case of KAP augmented Hamiltonian. So that's great. And in principle, that paves the way for integration of KAP technique with multiple, in principle, any electronic structure method. Again, so we just modify electronic Hamiltonian by one electron absorbing potential. And it has been done before, so there are multiple methods that have been combined with KAP, CI, SAC-CI, equation of motion CCSD, ADC, multi-reference perturbation theory, multi-reference CI. So why do we need anything else, right? So if you look at this set of methods, so it's notable, but still it's quite different from what is available, for example, for excited states. And moreover, if we look at these implementations, so the only one that is currently available or till recently was available for public use is the methods implemented in QChem. So it's KAP equation of motion CCSD and KAP ADC, which significantly limits kind of systems one can study. So what we thought would be ideal, as we have the powerful machinery and powerful codes that allow one to describe, for example, excited states, or in general, again, so any multi-state type of calculations for a bound electronic state. It would be ideal if we can reuse this powerful machinery and provide some external tool which can adapt these models and calculations for description of electronic states. So this is what we have done in this OpenCAP software. All right, so what enables these calculations is a projected CAP model. So what is done here and what is important. So in this case, we start from CAP independent calculation, multi-state calculation again. So in the context of today's talk, it's multi-reference methods implemented in MOLCAS, but it doesn't have to be. It can be equation of motion coupled cluster. It can be, in principle, even TD-DFT, and I will show some results later on. And then what we do, we project KAP augmented Hamiltonian onto this zero order basis and diagonalize. And from that, we get eigenvalues of KAP augmented Hamiltonian projected onto the subspace spanned by these zero order states. And in principle, what it means is the following, that we do single electronic structure calculation that doesn't know anything about existence of KAP. And that the other steps that we will have to do, we will have to be able to calculate cup metrics in the basis of this zero order state. But this can be trivially done as cup is one electron operator. And if we get state specific and transition state one particle densities, we can easily from the electronic structure calculations, which does not know anything about cup. So then we can do that. So this is in principle exactly how we approach this problem. So once again, so we do single electronic structure calculation, which does not know anything about existence of complex absorbing potential. We generate the basis of the zero order states. We calculate cap metrics in the basis of zero order states. We form kappa augmented Hamiltonian. We diagonalize this matrix and we get complex eigenvalues, which gives us real part of the real part as energy and imaginary part as a resonance width that is inversely proportional to lifetime. Okay, so that's the basic approach. And what is important here, as I will show, that the number of states, so dimension of these matrices are very small. So sometimes it's enough to have 5 states. Sometimes we will have to go up to 20 or 30, but again, so those matrices are very small matrices. So this step is essentially computationally, in terms of computational cost, is negligible. All right, so how does it work? And here I show the results obtained with equation of motion, CCSD, projected and conventional scheme, just to demonstrate that the projected technique works at all, and we can use it to extend existing quantum chemistry methods to metastable states. So there are, again, so commonly used small molecules used to benchmark performance of the methods for resonances. So N2-, CO- formaldehyde, acene, and benzoquinone. And we see that projected cup gives pretty much results that are very close to the conventional technique where we implement cup in the electronic Hamiltonian right away to start with at the Hartree-Fock stage. And again, so that's so these first 2 columns is what we have to compare, because this is apple to apple, same method, projected versus conventional. And yeah, so we are getting rather good agreement with experiment 2. All right, so it seems to be working. How many states do we need? It really depends. And for example, for N2-, we can see that if you look, for example, at the resonance energy, it's enough to get 5 states. So the same for width. So it's very small model space that we need to worry about. So in the case of CO-, we will have to go, depending on how converged we want to be, we might need to go up to 30 states. But the shifts are rather small already, starting from 10, so from 0.57 to 0.6 volt. So yeah, so the number of states in the correlated basis or zero order basis is very small to get the converged parameters of the resonances. Okay, so one concern one might have with this projected technique is how stable it is if you are thinking about potential energy surface, because in principle, one can imagine that might change molecular geometry and the number of states that is needed to obtain the converged result might change, or the states will have different character. So to test this hypothesis, we looked at the potential energy surface of N2-. So these are actually the results of multi-reference perturbation theory calculations. And we see that the resulting potential energy surfaces are A, smooth, and B, they are self-consistent in a way that their widths become 0 when their resonance energy becomes 0. So when resonance becomes stable, the widths become 0. And so in terms of the quality of this potential energy surface, so these are results of dynamical simulation on the potential energy surfaces obtained with multi-reference perturbation theory combined with CAP for vibrational excitation cross-section process upon electron scattering on N2. So what is happening here is we start in the ground state of N2, ground vibrational state of N2. It interacts with electrons, so electron impact, and the result of that formation of the metastable electronic state and its decay to ground state, so neutral N2 in different vibrational states. And what is shown here are cross sections are for this process for different final vibrational states, and we see that we have a pretty good agreement with the experiment. So not just these potential energy surfaces are smooth and self-consistent, they are also are of a good quality as confirmed by agreement with experimental data. All right, but so far this is just a general CAP technique. So how we can use this technique to extend existing implementation of the bound state methods to resonance, and again, so in particular, multi-reference methods are implemented in OpenMolCast to resonances. All right, so the idea is the following. So once again, we perform electronic structure calculation with the method and package of choice. We will need some information from it. We will need energies, and we will need densities, one particle densities, and transitional density matrices. We will calculate CAP metrics in the basis of these zero order states in our external OpenCAP software, and also in OpenCAP software, we will perform diagonalization of this CAP augmented Hamiltonian, analyze the data, and extract parameters of the resonance, so resonance energy and width. So more precisely, the workflow looks as follows. So we start with, again, electronic structure calculation, which gives us zero order electronic Hamiltonian. Typically diagonal, so energies. And again, so when I mean zero order electronic Hamiltonian, I mean zero order electronic Hamiltonian for projected CAP if we consider CAP as a first order perturbation. So it's not zero order Hamiltonian in multi-reference perturbation theory. All right, so we extract energies, we extract one particle density matrices and transition, one particle transition density matrices for the subset of states we work with. So again, typically rather moderate dimensions of the space from 5 to 15, 20. Then in OpenCAP, we evaluate CAP metrics in atomic orbital basis. And then once we have their one particle density matrices and transition density matrices, we can generate CAP basis in the state basis, CAP metrics in the state basis. We combine zero order Hamiltonian and CAP represented in the state basis to obtain CAP augmented Hamiltonian metrics. We diagonalize and we get resonance parameters, energy and width. And yeah, so all the analysis, again, also all the tools for the analysis of this CAP augmented Hamiltonian are also available in the OpenCAP software. All right, so what we have right now, so we have interfaces with OpenMolCast, so multi-reference perturbation theory, different flavors. So CI, SPICE, CF, and Psi4, equation of motion, CCSD, ADC, TDDFT. So multi-reference CI, the original interface was developed by the group of Spiridolo Matsika, which we were very happy to see with Columbus. So yeah, so now we have quite an extensive set of methods that one can use to describe electronic resonances, importantly, without any internal modification of existing codes. And yeah, so it works. So here we compare results projected, not projected, single reference methods, multi-reference methods, our previous implementation in Firefly package, and actually OpenMolCast, my apologies, for multi-state CAS-PT2. All right. So a bit in more details, right? So in terms of, for example, different flavors of multi-reference perturbation theory. So here I show results again for the same model system. So N2 minus CO2 minus ethylene and formaldehyde. And what we see here is that all different versions of multi-state CAS-PT2 give pretty close results. But one notion here that this is the case when we choose our active space and model space for multi-reference perturbations theory in a smart and consistent way. So if you have any questions and want to learn about it more, I'll be happy to talk about it. But if you do that, all multi-state perturbation theories give results that are pretty close, both in resonance energies and resonance widths. Now, so multi-state perturbation theory is great, but in some cases it's rather expensive, in particular if we eventually think, for example, about something like on-the-fly dynamics on the computed complex potential energy surfaces. So this becomes rather expensive. So cheaper alternatives would be highly desirable. And so one of their promising candidate in terms of the computational cost would be time-dependent density functional theory. So we looked at the pi star resonance in formaldehyde with various functionals, initially with 3 different functionals. And what we saw is rather discouraging. So yes, we are talking about electronic state in the continuum, so one would expect problematic behavior from TD-DFT. At the same time, we do use long-range corrected functionals, but the results we were getting were rather poor. So if you look at the CAP B3LYP and omega B97X, omega B97MV, so we consistently substantially underestimate resonance energy, and we consistently underestimate resonance width. And the similar trends we saw for other small molecules, CO- and N2-. And so then we found the paper by Mike Falsetta and Ken Jordan, where they looked at the similar approach, which is not cup-based, but stabilization-based, and explore different functionals. And what they found out that the only reasonable description of resonances they're getting with TD-DFT is when the functional they're using has 100% Hartree-Fock exchange, again, so short range and long range. And so this trend also held for CAP method. So what we see here is if you look at these functionals which have 100% Hartree-Fock exchange, they get pretty decent description. They give pretty decent description of resonance energy and width in comparison to other single reference methods. And what is interesting that, for example, for omega B97XD, which does have 100% Hartree-Fock exchange asymptotically, still what we are getting is rather poor description of both resonance energy and width. So yeah, so in principle, so this gives some positive news about using TD-DFT in the context of resonances, but one has to be extremely careful, and I think this requires further investigation. So to summarize, so we have developed this open CAP interface, which allows for extension of existing multi-state methods developed for bound electronic states without intrinsic modification of the software to description of metastable states. We have multiple interface, but again, so in particular interface with open molcast and multi-reference methods implemented there. So it can be easily installed, so pip installed. It supports different shapes of complex absorbing potential. I did not talk about it much, but we have different options here. It has all the tools to analyze the results of basically parsing CAP augmented Hamiltonian. I did not talk about this much, but people who are familiar with resonance calculations and know that to get resonance energy and lifetime, you have to analyze so-called eta trajectory, which is not always straightforward. So we have tools for that. Yeah, so, and in terms of implications for the method, so active space and model space choices have to be done differently in comparison to bound state, and they have to be done in a consistent way. So multi-reference CI methods are less sensitive to the active space choice, but at the same time, what we have found that multi-reference CI methods do not necessarily produce smooth potential energy surfaces. So we think how to properly explain that, and also they substantially overestimate resonance energy. And yeah, so exact exchange is crucial for TD-DFT to reproduce resonance energy and width. So the software is available at the GitHub. And so pretty much all the work I presented here was done by this very talented person, Jace Gavert, a former student of mine. And this research was supported by these funding agencies. So thank you very much for your attention, and I will be happy to take any questions.